So I imagine you already want to know what Jean-Bernard Léon Focault is doing this Friday night, but let me tell you some other awesome things that he did besides just this Focault pendulum. Yeah, he he realized that the gyroscope, this thing right here, could be used to show the rotation of the Earth much more simply the next year. He realized the gyroscope would work the next year to show the rotation of the Earth. Here's how this guy works. If you spin something, then it's spinning, let's say I'll turn it this direction. Okay, now it's spinning this direction. That axis right there is going to stay fixed regardless of the Earth's rotation. So you just get a gyroscope that's really high quality, and notice that if I try to turn the base, then the axis remains fixed. Probably some really interesting stuff about angular momentum going on right here, and worthy of several other videos. But Focault then created this gyroscope as a proof of the rotation of the Earth, and nobody does this though. They always do these Focault pendulum, which were way more expensive. Gyroscopes are cheap, you can get them as toys. Alright, so let's take this gyroscope out of here, and let me tell you something else about what he was doing. In Paris, he had found that the precession of the pendulum's apparent change in the path of its swinging was 270 degrees per day. And he found that in Paris, and he knew that in Paris, you had a latitude of 48.86 degrees north. And I want to help you understand why it wasn't 360 degrees per day. And the way I'm going to do that, get out of the way, Jean-Bernard. If you've got the Earth, and for the sake of ease, let's just put north up here and south down here. This sucker is spinning around counterclockwise as seen from above, so how can I show that? That side's going that way. That doesn't really show it. How about that? Yeah, that'll be fine. All right, you got an Earth right here, and if you're standing on the equator, can you imagine the Earth's got a big belt and you're standing right here, and you have a pendulum, you have a really long arm, and you have a pendulum that's swinging like this. Here's the bob, and it goes dot, 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 and so it's making this path right here. If it's swinging, now don't you agree the plane of the pendulum then would be my hand, if it's swinging like that? But as the Earth spins around, I'm going to go back around behind the Earth, and the plane will be like this, and then it'll be like that, and the plane's like this. Then when I get to over here again, I'm standing right here, and the plane of the pendulum is now like this. I'm holding the pendulum, and it's swinging like that. So the plane of the pendulum is definitely changing if we're not on the North Pole. That makes it complicated. But notice also that the plane of the pendulum, although changing, doesn't actually rotate as seen by this guy. This guy's gonna see always the same. So like, you never find Focault pendulums in Ecuador, for instance, or Equatorial Guinea, because they don't work there. Dang it. So we need to modify our equation for the precession of a pendulum, and we'll have to say that maybe it's, well, I need a function that's going to go from full precession up here, because it worked great on the North Pole, that was our example, to no precession right there. And I'm thinking I've already got this number, like this is the center of the Earth, and here's a line, and here's a dotted line representing my position. If I'm here in Paris or something, I guess it's 48, so a little bit north or in Paris. But anyway, you could put yourself right there, and you could call this phi, and phi represents the latitude. I'm not going to give you a lot of latitude on that decision because that is what the latitude is. So if you know your latitude, then you can find out how fast your pendulum will precess. I first noticed this at St. Louis, where was it? It was the St. Louis Science Center. They had a Focault pendulum when I was a kid, and I went there, and I thought it was pretty cool. They had a big circle, and they had all these blocks set up on the circle, and they had times when the blocks were going to be knocked down. So just for the sake of argument, now remember, it's going clockwise because the Earth itself is actually going counterclockwise under the rotation. So it started out going this direction. My pendulum might start in the morning going this direction, and then it will rotate, apparently, that direction, and it knocked down that block. And let's say it knocks down that block at noon. All right, and the next block knocks down 1 or something. But what I found really interesting was that 3 p.m. was here. Not here, but here. And that's because it wasn't going 360 degrees in a day. It was going to something. I mean, we're kind of close to Paris in latitude. I didn't even calculate what it is here, but I gotta give you an equation that's gonna go from full precession when theta is when phi is 90 degrees, and no precession when phi is 0 degrees. And that, I mean, if it's gonna do it smoothly, the best function for that is the sine function. So I'm gonna say precession rate, and I'm going to note that the precession rate is 360 degrees per day times the sine of the latitude. This gives us some really powerful stuff that we can do. I wonder if there was anything else I wanted to say. No, that's pretty much it. You can do calculations about anything right now. And, oh, you want to see something else cool? I'll show you something else cool at the very end. First, your homework. Your homework is: the notorious criminal Carmen Sandiego just landed on a desert island where her Focault pendulum precesses at 111.2 degrees per day counterclockwise. Uh-oh. Where is she? Hint, there is blue on the country's flag. All right, but here's something that I find particularly interesting. Here's something that likes to rotate, but not that way. It likes to rotate this way. No, it doesn't. It likes to rotate this way. And it will do that for a long time. So that's really interesting and probably worth some analysis. What are you, oh, now it's just wobbling. All right, it really does like to rotate this direction. It's like rather stable that direction, but it doesn't like to rotate that direction. It'll go and then turn back around. Awesome. So I told you that Focault was awesome, but did I mention that he measured the speed of light to 0.6% away from the currently accepted value in 1850s? Freaking awesome. And he discovered eddy currents. He noticed that a disc of copper would rotate more slowly. It had more resistance to rotation when magnets were nearby it. Ding! And he dramatically improved the telescope's mirror construction technique. There's a knife edge method attributed to him, and that greatly improved telescopes. So that's cool.